Hello, Hornets. Um, Tonight, what we're going to be looking at is the next step in our journey of differentiability. We talked about these two concepts of continuous and smooth in the last one. And one of the things that we saw when we were talking about smooth is that the derivative from the left has to equal the derivative from the right at every value. And those are two-sided limits. That means that the slope of the tangent line on the left side has to equal the slope of the tangent line to the right. And when they don't equal, we have something that is non-differentiable. Now, this can happen in equations like absolute values that we saw, and in which case we're asking ourselves, at what value is the vertex? And if you recall, the vertex point is at AB, and therefore we're looking for x equals a. At x equals a, the function will not be differentiable because the slope of the tangent line from the left does not equal the slope of the tangent line from the right. But we can also look at other equations, such as maybe something as simple as an f of x equals a 3x squared plus 2, and let's say a 5x. Now here, let's start at x equals 1, and let's go less than or equal to and x is greater than 1. Now, in order for us to have differentiability, we have to have first continuity. That means that wherever we stop in this graph from the left has to equal where we start the graph to the right. So we have this quadratic going up to 1, and this point happens to be at 1, comma 5, at which time the slope takes off, and we have the line at 5x. And this point also happens to coincide at 1, 5. Well, notice in this graph, the question becomes, is the derivative on the right equal to the derivative on the left? They both have the continuity. They happen to have at 5x will equal 3x squared plus 2 at x equals 1. They both equal 5. But that concept of smooth must also hold. And in order to do that, the derivative of this first equation has to equal the derivative of the second. Now, we've seen from our basic rules of derivatives that the derivative d dx of our 3x squared plus 2 is 6x. And at x equals 1, our answer is 6. Look what happens when we take the derivative of 5x. The derivative here is 5 at x equals 1, and our answer is 5. The derivatives are not equal, which means that this function is not differentiable. Okay? There are other times where we might have a situation where the function will not have a continuous graph. If we have a jump, it's not continuous, and we would stop there. There's no reason to check if a function is differentiable or smooth if it's not first continuous. So notice, let's just repeat what we have going on. Whenever we're looking at some functions that are graphically obvious, such as an absolute value, we might even locate something like the absolute value of x minus a over x minus a. And a graph such as this has two horizontal lines, one at y equals -1 and y equals +1. And that also wouldn't be differentiable because of a jump. There's two situations here. Then, if we have a piecewise function, we have to first check and make sure that that function is continuous. Where it starts, the other has to stop, and vice versa. And then we have to check the derivatives of both equations, and they have to be equal. If they are not equal, then it's not smooth, and therefore the function of f of x's graph is not differentiable at the value where they both meet. Now, keep in mind, if there's a jump or some kind of a gap, it's not going to work anyway. It's got to be first continuous. We often say that continuity implies differentiability. I think that's dangerous because some people will automatically assume that the graph, if it's continuous, must be differentiable. Well, are all rectangles squares? No, a finite group of them are. That's something you're going to need to think about here as well. Okay? Thank you very much. Take care and be well. Have a good night.